Yeah, thanks, Mark, for the nice introduction. Okay, so I'm Syamantak. I teach here at IIIT Delhi in India, and this is joint work with Suman, who is in Katana, Sainyam, who is a postdoc at U Chicago, and Sagar, who is a postdoc at University of Vienna. So my talk will sort of focus around this aspect of fairness in algorithm design, which, as you might all be knowing, is a growing area of research over the years, and so much so that now there are actually dedicated conferences which tries to address various aspects of ethics, bias, transparency, and accountability in algorithm design, and so on and so forth. In fact, it turns out that this is not only like an interest in the academia. Over the last few years, we have a lot of press coverage over incidents where, even in the tech industry, it was detected that there were bias in some of the tools that they were using. And so it turns out that as a community, the computational community needs to look at fairness in algorithm decision making. Today's talk is going to be about clustering. And as we all know, clustering is one of the classical aspects of unsupervised learning. We already in the last 3 talks, I think clustering showed up at least about a couple of times from what I remember. So, okay, so what is the classical notion of clustering? It says that, well, you have a data set, and I imagine that this data set is embedded in some sort of a high dimensional space. And what you have to come up with is a natural clustering of these points, let's say a K clusters. I give you a number K, you have to just do a clustering. And this seems like a natural clustering for, let's say, this set of points. Okay. But how do we bring in a notion of fairness to this problem now? Yeah. So this was actually initiated by a very important landmark paper by 4 authors, Cherichetti, Kumar, Latanzi, and Vasilvitsky back in 2017 New Rips. So what the model they proposed was sort of motivated by what is known as disparate impact doctrine. And in simple terms, what it says is the following, that suppose I call the data set of data points as population, and your population can be partitioned into a few protected groups on the basis of certain attributes, right? For instance, male and female could be one possibility, but there could be others as well. You could sort of divide up your population in terms of ethnicity and so on and so forth. Okay. And what the sort of disparate impact doctrine says, and sort of what these 4 authors also propose, is now you come up with a clustering where each cluster should have some fair proportional representation from each of these communities or each of these protected groups, right? So in a slightly more precise term, so suppose one of the protected groups, they form, let's say, X% of the entire data. Then you better make sure that in each of your cluster, there is at least, let's say, 0.8 times X% of data points which belong to this particular protected group. And this should be satisfied for each and every group, right? So I want to again solve the clustering problem, but now with these additional constraints in mind. And now clearly the clustering which we saw previously, that does not satisfy this. So if you look at this clustering, then the left cluster is heavily biased towards the blue points. So suppose there are only 2 protected groups in your population, the red and the blue. So the left cluster is heavily biased towards the blue points, and the red points are not represented at all, whereas the right cluster does just the opposite, right? So this is not a fair cluster as per our definition is concerned. On the other hand, this clustering on the same set of data, on the same set of points, is actually what we can call fair. Again, as far as the notion of these 4 authors is concerned, right? And but one thing which we need to understand now is that the clustering itself has changed. Yeah, is in particular, if you look at the sort of the stretch of each cluster, then the stretch of each cluster has grown. So the radius of the previous clustering was actually quite small compared to the radius which we have in these clusters now. And now this naturally calls for a trade-off kind of a question, which asks you to solve the clustering problem so that, let's say, the maximum radius of your cluster is minimized. So this is nothing but the classical K-center objective. And there are several other objectives, as you all be knowing. There is K-means, there is K-median. But for this work, we are just focusing on K-center, right? But now, in addition, you have to satisfy these fairness constraints. Okay. And now let me make this fairness notion a bit more formal. So suppose I have a few protected groups. Instead of two, I can have many protected groups in my community. And for each group I will keep two parameters. So let's say alpha and beta I. And now we'll have two kinds of constraints. The first constraint will sort of, it will restrict again over-representation of any group. So it will say that for each cluster, there could be at most an alpha I fraction of points which can belong to group I. And similarly, there is something known as minority protection, which says just the opposite, that should not be under-representation. So for each cluster, there should be at least a beta I fraction of points which should belong to this protected group BI, to the protected group CI. Okay, so that's the formal definition, and you want to solve the K center clustering problem. Okay, so now let me give you a very quick tour of how typically the algorithms, and this problem has been solved by several papers over the last 4 or 5 years, but all of them essentially revolve around this basic idea. So given this problem, so suppose in this example, there are 3 protected groups and you want 2 clusters out of them, and you want to solve a fair K-center clustering problem. The first step would be to just solve the vanilla clustering problem. Okay, so forget about fairness. You don't care about fairness anymore. Let's say you solve the fair clustering problem, but what you get out of this is you get a set of centers. Okay, so for instance, these are the 2 centers that you get out of this clustering. But of course, this is not the end of the story. You have to output a fair clustering, and the current clustering is not fair. But you still stick to these cluster centers. But in phase 2, what you now solve is what I call a fair assignment problem. So when these 2 centers are fixed, all you now need to do is make sure that you assign each point to one of these 2 centers, and the assignment should satisfy the fairness constraints. Okay, so these are sort of the 2 steps that goes into all these algorithms, right? And if you solve that, then it will actually give you these two clusters in case of this example. Okay, so just to summarize the steps once more. So step 1 is solve K-center, ignoring the color. Okay, so I refer to the groups as colors from now on, but groups and colors are interchangeable. So you ignore all the group thing, you ignore all the fairness constraints, and just solve the vanilla K-center problem. And in the next step, you solve this assignment problem. Now, it turns out that solving this assignment problem is not easy. In fact, one can show that in the worst case instances, this problem is NP hard. Okay, so but what one can do is one can formulate a linear program. They can solve the linear program and perform what we call a rounding step. So each variable of the linear program are rounded up to either a 0 or a 1, because these are decision variables. And one can prove that this gives you a 3 approximation to the K-center objective while maintaining the fairness constraints. Okay. So the challenge with this approach is that the size of this LP is very large. So solving LP is pretty expensive, as we all must be knowing. So, and the size of the LP sort of grows linearly with the size of the data set. So the question we address in this paper is, how can we make this process scalable? Is there any way to make this algorithm more scalable so that it scales to like billion size data sets and so on and so forth? Formally, what we do is we take these 2 models of computation, which have become extremely popular, especially because of the advent of big data algorithms. So one is the so-called MapReduce problem. So this is sort of a distributed computing environment where, let's say, instead of one machine, you have a bunch of machines, but each one of them has a restriction in memory, right? You cannot fit the entire data into the memory of one machine, but you can distribute it over all of them, and you can process the data in parallel. And then there is a central machine which also has restricted memory, but these peripheral machines can sort of communicate with this central machine back and forth. Okay, so the idea would be to solve the problems efficiently by minimizing the number of rounds of communication. Okay, so that's one model. The other model, what we consider, is the so-called streaming model, where the data points are not given to you all at once. In fact, you do not have that much of memory to hold the entire data set. Rather, the data is given to you in the form of a stream, so you can retain a part of the data at a specific point of time. You can perform some computation and move ahead and so on and so forth. Okay, so these are the 2 settings where we consider the fair K-center problem. And here are the results. So what we show is that in the MapReduce model, we can achieve a 9 approximation. So please note that in the sequential setting, the classical setting, we had a 3 approximation, but now our factor is slightly worse. So it's a 9 approximation. And the space that we use on any particular machine, that is sort of the best that you can hope for, right? Because if you have m many machines and you have a data of size n, then at least, some machine has to have n over m amount of data, right? And the second term is also interesting because this sort of says that, so m is the number of machines, k is the number of clusters, and this gamma term is the total number of protected groups that are there in your data set, in your input, right? So note that this term is not linearly dependent on the size of the input as such. It's logarithm in the size of the input, okay? Similarly, for the streaming setting, we have a 7 approximation, but this is a 2-pass streaming algorithm, which is not exactly the classical streaming setting where you can only make 1 pass, but we are allowed to make, let's say, 2 passes. And the space that we need is slightly worse than MapReduce because there is this log delta term where delta is some number which is dependent on the metric space that you are talking about, okay? So those are the results. And now let me give you a quick overview of what is our basic insight. So the basic insight is as follows. So let's say, again, I'm talking about the MapReduce model now. So you have these peripheral machines and your data is distributed over all these machines. So the first step is, and let's say I want to solve the k-center problem with k equals to 3. And I have these 3 protected groups, red, green, and blue. So the first step, what I will do is I will just solve the vanilla k-center problem on each of these machines individually. So I don't care about, solving the whole problem altogether. I just sort of solve in these pockets, okay? And now after I have identified these local k-centers, I will use them to sort of represent the entire data. So think of these k-centers on each of these machines as some sort of a summary of the data that was contained in them. And this summary should also contain the color information, right? So we maintain this color information as some sort of a weight. So unfortunately, I cannot go into the details of what these weights are. And then we send the total, all these summaries from these machines to the central machine. Remember, in the MPC, in the MapReduce model, there is a central server sitting in the middle, right? And there we solve something which we call the weighted fair clustering. And this algorithm, of course, draws inspiration from the previous algorithms that were there. But because of these weights, now we had to modify it quite a bit. And we managed to prove the approximation guarantees sort of that I showed. So the major gain, as I had mentioned a few slides earlier, is that the main bottleneck of these fair clustering algorithms is that they solve linear programs, and the size of the number of variables, they sort of grow with the size of the input. Whereas in our case, once you do this summarization and solve the weighted fair clustering on the central machine, then the number of variables in your linear program is much, much smaller. It just depends on the number of peripheral machines, the number of clusters you want, and the number of protected groups. So typically all these are smaller compared to the size of the data set, right? Okay. So quickly let's see a couple of slides on the results. So this is our result in the MapReduce setting. So we compare ourselves with 3 algorithms. So VKC and VKC MPC, they are just vanilla K clustering problems. Algorithms, so they do not address the fairness aspect, and which is why, of course, they are faster compared to us. But the main benchmark that we compare against is this KFC algorithm, which is the current state of the art for fair k-center problem, which gives a 3 approximation. And as you can see that we are as good as that algorithm, at least as good in terms of the cost of our objective, whereas in terms of running time, we are actually much, much faster compared to KFC, right? So this pink line is KFC and the green line is us, and we beat that as the size of our data grows and the number of centers grow. So, okay, excuse me for that. So let me also mention the size of these data sets. That is a constant. So in the first plot, this G plus, this is like data which is of size roughly 100,000. Whereas the second data set is roughly of size like 1.6 million points with about 10 dimensions. So both of these are from social networks. Okay, so a similar trend also follows for the streaming setting, and I just skip it for the interest of time. But there also we have a benchmark, and we see that In terms of cost, we are sort of as good as the benchmark, but in terms of runtime, we are sort of better. So in conclusion, what we present here is sort of a general technique to scale fair center to million or even, so we also ran experiment on a data set which is 50 million in size, although that was not exactly a web data. So we gave approximation algorithms in both the MapReduce and streaming setting. And in fact, I think the key takeaway of our work is that although we presented the work as algorithms in MapReduce and streaming, both of these algorithms can be also simulated in the sequential model in order to speed up your algorithm. And finally, we showed some empirical evidence that our algorithm is not only theoretically sound, but also effective in practice. So thank you for listening.
Many thanks for your presentation. Are there questions from the audience? Well, let me start with one question first, which was directly striking me. I mean, your results are really impressive in terms of your speed gain. And I mean, my question is, you achieve the same, basically the same quality than the performer, but you are orders of magnitude faster. Right. So what is the intuition? So can you just give us intuition how you beat it, actually?
Exactly. So the intuition is, if we talk about this KFC algorithm, for example, so the point is that this algorithm sort of works on the entire data together, right? Which is why when they're solving the LP, the linear program, the number of variables in the LP, it sort of scales linearly with the total size of the data.
I see. Okay.
Whereas what we propose is you first form a summary of, as many summaries as you want. So there is a trade-off between the number of summaries you make versus the number of variables you will have. So this M is sort of the number of summaries that you are making, which is the number of parallel machines. And then you gain a speed up in two ways. First of all, because you are solving a lot of stuff in parallel, there you get one speed up, of course. And then the LP is also much smaller compared to the LP which they had.
Which particularly kicks in if the data set gets larger and larger, right? Then you basically win a lot.
Yeah.
Okay, that's pretty cool. So thanks again for this very nice, interesting presentation.